Again, based on some of the discussions on Piazza, I thought it would be useful to do some more detailed examples looking at problems that are related to here free undamped vibrations. There'll be a total of 3 new videos done this week. And it's really just the standard problem with standard twists. And standard twists just mean we expect certain things at this point in the course, and I'm trying to sort of highlight those so that you're aware of them and know how to deal with them. And again, how to really focus in on these problems. They're often, when you look at the motion, it looks complex, but it may not be that bad after you try it out. So we have here a pulley system. It consists of 2 pulleys, one which is free to move up and down, one which is attached to the ceiling. A mass is attached to one of the pulleys. That mass is 20 kilograms. The radius of the 2 pulleys is given as 0.3 meters. And you have a spring at the very bottom where you're going to get stretch. And that has a spring constant of 600 newtons per meter. You're given the axial directions x and y and g, which is acting downward. Now it's important, and really we should do this more often, but to say that the pulleys are massless. And what that does is sum of forces equals ma becomes 0 because mass of the pulleys is 0. So if I look at pulley A, which is defined on the figure here, I have the same thing, which is direction y down. I have 2t up, 2t down, and sum of forces in the y direction is equal to 0. Minus t plus 2t then equals 0, and sort of no surprise. So I know what the tension is in the cable. If I look at the mass, I have the weight acting downwards, and because the mass is not massless, it's going to have an acceleration. That's going to be my double dot. I have 2t, which is acting upwards from the two wraparound lengths of the pulley, and I have the weight acting downward. So that's equal in terms of the 2 halves. Finally, I have the last pulley, pulley B, and there I'm going to have again 2t, which is acting upwards, 2t, which is acting downwards. And it's again 0, and that's because the entire system is again, for this pulley, for pulley A and pulley B, are massless. And lastly, the spring. And the spring is pulling upward, and the spring is responsible for all of the stretch. You've seen at this point a number of problems looking at stretched springs and pulleys. The spring is often used to make up for the length of the pulley, and in so doing, it takes up the full length required. So if I look at pulley A, for example, which has a wraparound length of 2, I'm going to have a delta x, a delta x. So I have to take 2 delta y, in this particular case, and I'll get t equals 2ky. So I know tension is equal to 2ky. Sum of forces in y is my double dot. I'm using y as my direction of motion. I have 2 times t, so minus 2ky plus mg equals my double dot. So 4ky negative plus mg equals my double dot. Now, in order to make this all work out really nicely, I need to get rid of the mg terms, and I have to recognize that 4ky equivalent equals mg. That's the static case, and y equivalent is mg over 4k. Well, in that case, I have no motion. I substitute back into my expression, and I end up with the dynamic case, which is the my double dot plus 4ky equals 0. I've just switched y's here, which is probably poorly done, but what I should have written maybe is y dynamic plus y static, and the y static or y equivalent is the one that goes away. Omega n of this system right away I can see is 4k over m, and I can solve through for it. For the next one, I have an example that's again sort of similar. I've got a spring, it's attached to a wall and attached to a cord. There's a disc, and it rolls without slip on a block B. What is the natural frequency of the system? The other thing I'm told is that it's frictionless between B and the ground. So if I look at this particular figure, on the left-hand side, I'm going to put all of my kinetic terms. On the right-hand side, I'm going to put all my kinematic terms. And when I do that, first of all, I have the forces that are acting from the spring, Kx. I have the weight, which is acting downwards. I have the normal between block B and A, and I have force of friction, and I'm going to assume it's acting to the right. The next thing I'm going to do is put the terms that are appropriate to block B. So I've got force of friction, and because of Newton's third law, it has to act in the opposite direction. I have the normal AB, which is acting downward because it has to oppose the normal BA. And then I have the normal and mass of BG, weight. I don't have a friction force between the ground and B because I know that that's frictionless. I do have a friction force because I know that there is rolling without slip between the disk and the block B. So remember Newton's third law, and this is really the main reason why I wanted to do this particular example. If I look at the other terms, I have angular acceleration, translational acceleration, and I have translational acceleration for block B. So I have all of the terms here. I'm ready to go. They're equal. They're equal. There you go. Some moments about A. Here it's only going to be about its center of mass. So it's just going to be force of friction times R. And it's equal to IAG theta double dot. And I just decided to make it clockwise as positive. Force of friction minus Kx equals MAX double dot. And then here I have minus F MBX double dot. I also know that x1 equals x2 plus x1 with respect to 2, or x1 double dot, the acceleration terms have the similar relationship. And I can write that friction as x1 minus x2 over r. So this is one of the reasons why I make it positive, because now I have all the same terms in the same direction. If I substitute in terms, I have minus force of friction, which is equal to MBX double dot, which is given over to the left. And we can get minus MBX double dot minus KX equals MAX double dot. So really what I'm trying to do is get an expression for x1 in terms of x2. So I have MBX2 double dot R equals IAG over R, x1 double dot minus x2 double dot. Substituting in terms, IA over R, x1 double dot equals MBX2 double dot R. Okay, IAG over R, x2 double dot. Okay, I've got a relationship out of the two. I have all the terms, substituting in expressions. I can sort of substitute things in, and I get IAG x1 double dot is equal to MBR IAG over R times x2 double dot, which is minus 1 over MB KX MA x1 double dot. This is going to get confusing, but that's really what that is. Now, doing that, I have everything in terms of x1, and I have this other term, which should be x1 also, but it's IAG r squared plus MA, MAG, IJG, ME r squared, x1 double dot, plus K1 times IAG over MB r squared times x equals 0. Substituting in those two terms, I know that the term in the light blue square is going to be my K equivalent. The term in the dark blue square is my M equivalent. Substituting in terms, I end up with the natural frequency of the system, the natural circular frequency depending on which book you're using, but natural circular frequency for Merriam and Craig, and natural frequency for Hibbeler. K is equal to MB r squared plus IAG, IAG, MAB plus MA plus MB plus MA MB r squared. Finally, a rigid body example. So this is a case where I'm looking again at an L bar. You've looked at L bars before. I have it attached to the ceiling and it's pinned at point A. The bar is 4 meters from A to B and 6 meters from B to C. The mass of the link is 40 kilograms. And the bar is slightly displaced from its equilibrium, released, and you're asked to find the period. So let's start by finding the center of mass. So this is often a problem with these types of problems. This is a pendulum in a very simple way, and if it's a pendulum, it's going to essentially rotate from A to its center of mass. So I need to find where the center of mass is. So I've defined a coordinate xy, which is convenient to this. I know the total length is LAB plus LBC. I can substitute in all of this and get xg, which is xAB MAB plus xBC MBC over a mass total. Substituting all the terms in and recognizing that the link AB is located at x equals 0, I only have to worry about the center of mass of xg, and xg is equal to 3 meters to the center of mass and 3/5 of 40 kilograms over 40 kilograms, and that equals 1.8 meters. Same thing with yg, and I get 0.8 meters. Now for the length BC, it is equal to y equals 0, and I can just substitute in the y term there. Now, if I go on a little bit, I can say that the distance from A to the center of mass of the link BC is going to be 5 meters, because it's 4 meters from A to, or 3 meters from A to B, or sorry, 4 meters from A to B, and 3 meters from B to the center of mass. So 3, 4, 5 triangle. I can use for AB a pinned slender rod, 1/3 MAB LAB squared, and for the link BC, I'm going to use 1/12 MB LBC squared plus the distance L2, which is that 5 meters, to get an IA of 757.33 kilogram meter squared. Now, everything is rotating about that center of mass. So I need to calculate L3. And L3 I can calculate as being the distance 3.2 meters, which is the distance from A to the location of the center of mass along A, so along the y-axis, and 0.8 meters along the x-axis. If I substitute in terms, I have IA theta double dot mg L3 sine theta equals 0, substitute in everything, and I have a natural frequency of the system mg L3 over IA. The period of this is 2 pi over omega n, and that's 4.6 seconds. These are 3 undamped examples, one with a rigid body. They're kind of good to sort of look at those. And I kind of encourage you to be very comfortable with these types of problems. Thank you very much, and we'll talk again.